This is an optional assignment. If you feel that you have done enough work for this class, that's silly. I need to get stuff. Hello everyone, welcome to the tutorial for Optional Software Homework 2. This will go over some sample data sets that will help you to actually do the analysis for the assignment itself. This is an extra credit assignment. For those of you who think that you need some extra credit, if you've done all of the assignments thus far, you do not need to do this. However, for those of you who do not want to submit this assignment, I recommend that you watch it because I think that it will help you to do some of the questions in the final exam, quiz 4. So without further ado, let's continue. Here are the instructions for the assignment. You'll be submitting 7 files for this assignment. There will be 6 JASP output files, which will be in HTML format, and I'll show you how to export those later. And there will also be 1 Microsoft Word file. I recommend you just modify the Word file that you see in front of you now. That will contain the information and instructions for the assignment. And because Blackboard cannot accept HTML files, please email me all of the files associated with this assignment. So there will be 6 HTML files and 1 Microsoft Word file. For the files you need, they'll all be listed and outlined in the assignment section of this document. The due date for this assignment will be Saturday, May 15th at noon. And this will also be the due date for the final exam, quiz 4. There will be 2 data sets associated with these assignments that are available along with this instructions document on the assignment module. But let's actually begin with the samples data sets that I'd like to show you. So there will be a link on the YouTube video you're currently watching to a Google Drive folder containing the following 5 data sets. We won't be going over all of them, but I recommend that you familiarize yourself with them so that you'll be better able to do the analyses that are requested both in quiz 4 as well as this assignment itself. So all of these assignment documents, both samples and the ones outlined in Optional Software Homework number 2, are in the CSV file format. That's the comma separated value format. That is the universal format for data, and it is one that JASP accepts. So in order to open up a CSV file, we're going to go into JASP, open computer. Let's find our documents. So for the first one, let's go over the independent samples t-test example that we went over earlier in the class. So the first thing you want to do once you open a document in JASP is to inspect the variables that JASP has assigned to the variables in your study. So to refresh your memory, this particular data set is referring to fictional data from a study of rats put on one of 2 kinds of diet. There is a high-fat, high-sugar diet and a normal chow diet. That was the sorting of the 2 groups of rats into the type of diet they received. And there was also a separate variable that measured the weight of the rats in grams after having been on the diet. There were 20 subjects, 20 rats in this group, 20 subjects, 20 cases, and the diet condition, the normal chow, NC, or the high-fat, high-sugar, HF/HS conditions, those are a categorical nominal type of variable. JASP has assigned that correctly. The weight variable is a numeric scale type variable. JASP correctly did that as well. And for this particular example, this data set was used as an example of an independent samples t-test because we had 2 groups, and the 2 groups were sorted into different diets, a numerical type of variable, and they had 1 dependent variable, which was numeric, associated with them. So in order to do this analysis, we go to the t-test icon in the top of the screen, and choose Independent Samples t-test. So once you choose the kind of statistical test, you're brought to this middle panel in JASP where you have to assign the variables into two boxes over on the right. The variable under assessment is weight. This is the dependent variable, and you can tell by the little ruler icon on the bottom right side of this box that it accepts only numeric scale type variables. The grouping variable can be either nominal or ordinal, but in our case, it's a nominal type variable, and it'll go into this grouping variable box. Notice that there are three different options for the type of t-test. We'll choose student t-test, which is the standard one that we learned about in class. Next, you'll see that there's an option to select the kind of test you want to do for your research hypothesis. You can predict that group 1 and group 2, the two different diagroups, will simply not equal each other, which was what we called a non-directional type of test that's analyzed using a two-tailed test. And then there's two different kinds of one-tailed tests depending on whether you predict the first group, one group, to be higher or lower. And remember that the group 1 and group 2, unless you specify it directly, JASP will interpret group 1 as the group whose alphabetical order appears before group 2. So in our case, the HFHS group will be labeled as group 1, and the NC group will be labeled as group 2 because H comes before N in the alphabet. In addition, we also recommended doing these assumption checks. So it's the assumption of normality and the assumption of equality of variances were two assumptions that were required for the independent samples t-test, specifically the student's type of t-test. And let's also select some additional statistics to be included in your output. These are things that we would have included if we were to do this by hand. We would have just found them, such as we can choose an effect size measure. This location parameter actually refers to the mean difference score that we calculated between the two groups. We can get descriptive statistics, plots, and that's pretty much it when it comes to the independent samples t-test. If you see it on the results panel on the far right of the screen, it shows you a table just summarizing the results of the statistical test. It tells you that this was a student's t-test rather than the Welch or the Mann-Whitney type. It gives you the t-statistic for your sample. In this case, the t-statistic that represents the mean differences between the normal chow and the high-fat, high-sugar chow diet groups. It gives us the degrees of freedom for the experiment. There was a total of 20 animals in two groups, and the degrees of freedom is calculated by n-1 for both groups, so 9 plus 9. And we also have a p-value associated with this test. And what we find is that in this test, the p-value is 0.077, and depending on what we chose as our alpha value, the p-value would tell us whether or not this was statistically significant. And given that the alpha values chosen most frequently for our studies were 0.05 and 0.01, a p-value of 0.077 would not be statistically significant with the conventional alpha values we've done thus far. And then it gives us some mean difference and standard error of the difference that we asked for with these additional statistic options. And it also gives us the confidence interval around the mean difference scores. And the confidence intervals range from -1.22 to 20.048. And these difference scores, the fact that the confidence intervals are so large and that they contain a score of 0, which means a mean difference of 0, that leads us to interpret that there is, in fact, it's unlikely that there is a statistically significant difference between the groups because the 95% confidence interval tells us whether or not the difference between two groups is likely to include 0. no effect. And down here, it gives us some stuff about the assumptions checks. If you're interested in learning more about that, you can review the YouTube video of the class on the independent samples t-test, where I discuss how the normality tests and the equality of variance assumptions influence our interpretation of the independent samples t-test, which is to say, are they appropriate or not? Here, because the p-value does not achieve statistical significance for the Shapiro-Wilk test of normality, nor for the Levine's test of the equality of variances, that is sufficient for us to assume that both of the assumptions of normality and equality of variances were satisfied for the sake of the student's t-test. And then it gives us descriptive statistics, just like we learned how to generate back at the beginning of the class, and it gives us a basic plot of our data, where we have the high-fat, high-sugar diet child group and the normal child group represented by 2 points along a y-axis representing the dependent variable weight. And it also gives us the standard error of mean. And notice that the large overlap between the error bars of the 2 diet groups strongly indicates to us that it's unlikely that there's any statistical significance. All right, so that was the independent samples t-test. And in order to export the results of this study, or the results of this analysis rather, what we would do is we would go to those 3 bars at the top left pane of the JASP panel. We would then click export results, not export data, but export results, because the data would just be the rats themselves. We would choose the file we want to export to. We choose, there's only one type of file that you're allowed to save it as, an HTML type file. And in the actual assignment document, I ask you to select a specific file name for each of the analyses you send me, because that'll just help me to grade them more easily. But here, let's just keep them as the default type. So with that, I've exported the results, and this means that I can review this data whenever I want. So now let's open up a new JASP dataset, this time with the correlation, regression, prediction type of data. Hold on a moment. All right, next we're going to look at a data set that is an example of the correlation, prediction, and regression type problems we learned about. So once again, in order to open up this type of data file, we're going to go up to the top left panel in JASP to these 3 horizontal bars. Go to Open, Computer. We'll find the data set we'll be working with. In this case, we'll be working with a data set called Grades in TV, which I'll explain in just a moment. Whenever you open up a new data set, JASP will open up a new window because it assumes that you want to have multiple analyses open at the same time. So the first thing we see is that we have our data. There are 25 cases, and they're representing students who report the number of hours they spend watching TV every week, as well as their grades in some class. These are both numeric type variables, and JASP has correctly identified them both as scale variables, as shown by the little ruler icon, and 2 scale variables that are both numeric. This is what you would use for a correlation type of analysis. So in order to do the correlation type of analysis, we're going to go to the regression tab in Blackboard. We'll go to first, well, let's go to linear regression. And in this case, I can tell you that this study was interested in the effect of the number of hours spent watching TV on students' grades. So what we have is grades is the dependent variable, and as what we call covariate, we have TV. And before we can go on to look at the right-hand panel, let's actually add some little bits of information we want to include in the right-hand panel. So in the first option, model, there really is nothing to include. I make sure that include intercept is checked. There are things you can include here, but the only one that I want you to click is descriptives. Descriptive simply gives you an overview of your data, and often that's useful in order to figure out whether there was some kind of error that you need to address. For method specification, you don't need to choose anything. And for plots, unfortunately, the linear regression option in JASP does not offer you the sort of simple correlation between two variables plots that I asked you to produce. But what it does offer you is, first, it gives you the value of R, the correlation coefficient. Here it's shown by capital R, but it actually is little r. And what we find is that for the variables grades and TV, the linear correlation is 0.535. And since it's a positive correlation. Linear regression gives you this thing here called the ANOVA model. Because we only have two variables, it's not something we are going to be looking at. So let's skip down to the coefficients table, which gives us two values that are very useful to us. So if you recall, one of the things that we often wanted to know for the sake of predicting new data points based on our current correlation model is we need to know the equation of the regression line. So that regression line is given by y equals ax plus b, where x and y are values of your independent variable x and dependent variable y, but a and b need to be determined experimentally. A and b need to be, calculated separately. It's a hassle to calculate them by hand, especially if you have a lot of data to work with. So JASP is quite useful because it actually gives you those values of A and B in this coefficients table. This first part of the table, the null hypothesis, ignore everything here. Focus instead on this alternative hypothesis, which gives two values in this second column. It gives you the intercept, which is that b value in the y equals ax plus b regression line equation. And the a value, the slope of the regression line, is right below it, and it's minus 0.605. And since these values of a and b are all you need to know in order to predict what a value of y will be for a given value of x, the regression options in JASP are very, very helpful. And down here is just descriptive statistics that show you the sample we had. We had 25 subjects, and each subject contributed 2 scores. So for our 2 variables, there are 25 scores each. And it gives you the mean, standard deviation, and standard error. But one of the other things that I would want you to produce for any question about correlations is the plot of the 2 variables. To do that, go to the regression icon in JASP again, and choose correlation instead of linear regression. So correlation will just open as a separate analysis. The previous analysis with linear regression will still be there, but it will be grayed out because JASP assumes you aren't currently working on it. The correlation analysis is much more tractable in JASP. You simply take your 2 variables, TV and grades, move them over from this left box to the right box where your variables go, and choose the following things. Calculate Pearson's R, the correlation coefficient. For this alternate hypothesis, there will be a question, I believe, on both the exam and in the optional software homework 2 assignment, where I ask you, for the sake of testing a correlation, to assume either a two-tailed test, a non-directional hypothesis, or one of two kinds of one-tailed tests. So let's say for this particular question, you, the experimenter, don't have any kind of prediction of how the number of hours spent watching TV will affect grades. So in that case, you have a non-directional hypothesis, and the alternative hypothesis you'll choose is simply that the two variables are correlated, but you're not specifying whether they're correlated positively or negatively. So correlated as an alternative hypothesis option represents a non-directional hypothesis, which is conceptually very similar to the two-tailed tests we learned about for everything from z-tests to t-tests. So for the additional options, to report significance, that means we wanted to do an analysis of whether or not the correlation is significant, which is something I want to know. And let's also produce a scatter plot. The scatter plot is the one thing that the correlation option in the regression icon and JASP does that the linear correlation one does not. So let's go down and see what we've got. So this is quite messy here, and let's see whether we can clean this up, because currently the variables are there, it's just they are scattered across this output panel. So during our last lecture, I forgot to show you how to sort of make sure that this correlation plot is represented in a way that looks nice and neat and is easy to read. And to do that, you simply need to look at this additional options panel and be sure to click Display Pairwise as the option. And Display Pairwise is essentially telling JASP to associate every case, so every student who submitted a data point for number of TV hours watched and the grade, just to tell JASP, interpret that as a single experimental unit that has a pair of scores associated with it. And this will cause JASP to understand the kind of scatter plot you want to produce. So we have TV, number of hours spent watching TV, represented on our x-axis. That's our independent variable. And our dependent variable, the exam grades, is represented on the y-axis. And you see there are 25 icons, 25 points on our scatter plot representing the 25 students who submitted scores. Each had a pair of scores. They had a TV watching score and a grade. And all of those individual scores are represented on the scatter plot. And the line that you see going through the points and going through the scatter diagram, that is the regression line. The regression line, as you can see, is negative. We see that as the number of hours spent watching TV increases, grades decrease on average. So this is a negative correlation. But one of the questions we might have is this correlation significant? And before you answer a question about the significance of a correlation, you need to know two things. First, you need to know what your alternative hypothesis is. And remember before, we talked about our alternative hypothesis being a non-directional hypothesis where the prediction was that there would be a correlation, but you're not predicting positive or negative specifically. And the other thing you need to know is the alpha value. So in the correlation diagram, in the correlation table up here, it gives us our Pearson's correlations. For the correlation between hours spent watching TV and grades on the exams, the Pearson's R is minus 0.535. That makes sense because it's a negative number and it's representing the fact that this is a negative slope of the correlation line. As TV hours increase, grades decrease. Your classic negative correlation between two numeric variables. And the p-value is given by 0.006. So if, for example, I asked you, assuming an alpha value of 0.01, would this p-value be significant? Would the correlation be significant given a non-directional hypothesis and an alpha value of 0.01? The answer is yes, it would, because the p-value here is less than our alpha value, and because it's less than our alpha value, that causes us to reject the null hypothesis, which for a correlation kind of problem is that there is no correlation. So you would instead conclude that there is a correlation, and in fact it is a negative correlation. And just to return to the model that we created using the linear regression options in JASP, what you see here that I highlighted as the A and B factors in the regression equation, 89.132 would be the value of B in the regression equation, which is the y-intercept, and TV watching, and this minus 0.605, that is the slope of the regression line. So what you see here, this regression line, this would be represented by y equals ax plus b, where a is minus 0.605 times x plus a value of b as 89.132. And that 89.132, which is called intercept, is the y-intercept. And you can see that if you were to extend the regression line up to the value where it crosses the y-axis, it's right about at 89.132. So that is pretty much all you would need to know to generate the output that I asked for a correlation regression style question. And to export your data, once again, click on the top 3 horizontal bars in JASP, choose to export results, not export data, go to Computer, select the file, and then save your data, save your report as an HTML type file with the file name I tell you. So that's the correlation regression style questions. And now let's wrap it up with a chi-square type of question, a chi-square kind of analysis rather. And to do this, we'll open up a third file. For this one, it'll be similar to a kind of question that I asked both on the exam as well as in this optional software homework, which is about class level. Let's wait for it to open. So what we have here is a chi-square and goodness of fit analysis question. Like always, let's inspect to make sure that JASP has selected the correct kind of variable, and if not, change it to the correct kind of variable. So what we have is 26 students, and these 26 students are represented, or each of the variables that a student contributes is a nominal type of variable, which is what their class level is. It's not numeric, it's not ordinal, and JASP has correctly identified that this is a nominal type variable. And now that JASP has correctly identified that, we can move on to the analysis of the chi-square goodness of fit test. To do this, we'll go to the Frequencies tab in the top panel of JASP and choose, for the sake of this test, a multinomial test. So this is a multinomial test because class level includes more than 2 values. So class level is either freshman, sophomore, junior, or senior. If it was just between 2 variables, we could use the binomial test, but because we have more than 2 variables, the multinomial test option is the one we're choosing. So the multinomial test is also analyzed by the chi-square statistic. We have only one kind of variable, and this is going straight into our factor section. So comparatively, this is a very, very easy kind of test to run. So all you need to do is move the one variable into the factor box over here, which you can see accepts nominal or ordinal scale variables. And immediately, it does the chi-square goodness of fit test for you. It gives you a chi-square score of 9.769, and it gives you a p-value of 0.008. But there's actually something that is not shown here that I want you to pay attention to. It tells you that the degrees of freedom is 2. And if you recall, for a chi-square goodness of fit test, the degrees of freedom is calculated by the number of categories minus 1. So if there are the number of categories for the variable class level is not 3, it's actually 4. So this is an example of how using JASP or software mindlessly can get you the wrong information and give you the wrong output. So in order to actually do this test correctly, what we would need to do is we would need to take our chi-square, we need to ignore this chi-square statistic and instead use a new chi-square. We would have to sort of do this using another software because JASP is not able to do this correctly. But assuming for the sake of this analysis, we have a class that consists of only 3 kinds of class level. There are literally no seniors, and we're not including those in our analysis. We have a chi-square test statistic of about 9.77 with 2 degrees of freedom. Because remember, in this fictional example, we only have 3 categories of class level, not the 4 that most schools have. So in this example, for a chi-square comparison distribution with 2 degrees of freedom, for a test statistic that is 9.769, this gives us a p-value of 0.008. So a p-value of 0.008 is below the conventional alpha value thresholds of 0.05 and 0.01. So if you recall the interpretation of the chi-square goodness of fit test, when the p-value is significant, the interpretation of the chi-square test is that there is something other than something non-random about the distribution of the different values for the variable class level. So remember, the chi-square test compares your expected frequencies for a given variable and the different values it can take on to the actual observed frequencies in your data set. So here we have the options, and the options are fairly straightforward. I recommend that you choose descriptive statistics and as well as reporting a confidence interval. Next, we can just have a plot of our data. And so we have 3 different levels for class level. We have freshman, junior, and sophomore. Note here, once again, JASP is ordering these not in the same order that we might intuitively expect freshman, sophomore, and junior to be ordered. We'd expect freshman, sophomore, junior. But just like with the independent samples t-tests, assignment of groups, JASP defaults to alphabetical order when creating this plot, as well as creating the order of in which it presents the rows in the descriptive statistics. So one of the things that I will ask you about, both in the exam and in this optional software homework, is what if instead of expecting simply an equal distribution of all of these 3 values in the data set, what if we instead expected that there was just in the population being sampled from twice as many sophomores as there was juniors and freshmen in whatever population being sampled from. So what you would do is you would choose as test values, instead of equal proportions, which is the default, you'd instead click this expected proportions for a chi-square test, and it will open up this table where you can adjust the relative frequencies of your expected frequencies. So here, just by default, they all have the value of 1, which is when you expect an equal probability of each of the 3 values being sampled from. But just to go back to my example, what if we expect twice as many sophomores as either juniors or freshmen in the population? So by changing that value of 1 to a 2, what you see is that the plot remains the same, but if we go to the value of chi-squared in this test up here, we actually find that it has shrank from about 9.7 to 4.3. And it shrank because the expected value of the chi-square test statistic, the expected value of the number of sophomores in this sample now more closely matches the expected values. So when the observations are closer to your expected values, then the chi-square test statistic decreases. And when chi-square test statistic decreases, that means that it is more likely that you will fail to reject the null hypothesis. Your data is less surprising because your observations more closely match your expectations. And exactly as I would predict, we see that the p-value, which was formerly significant at either alpha of 0.01 or 0.05, is now not significant at either of those conventional p-values. So this is the sort of significance of stating your expectations about the distribution of each of your values for your variable, because if you choose simply to expect an equal proportion of each of the values, you might end up doing a chi-square test where you incorrectly infer that your data is very surprising. But if you sort of approached your data with expectations that were informed by more realistic understanding of what the population being sampled from was like in terms of the relative distribution of each of the variable types, it would not actually be surprising. And that was the lesson behind that. So that's all of the output that I would want you to include for the chi-square goodness of fit test. And to export this, once again, you go to the options on the top left, choose to export your results, select a file on your computer where you want those exported files to go, click Save, and that is all you need to do in order to complete the independent samples t-test kind of questions, or the correlation regression style questions, or in this case, the chi-square goodness of fit type of questions. Your final exam, quiz 4, will not include any independent samples t-test JASP analyses, but there is one question about that on the optional software homework too. So I hope this is helpful to everyone, and please let me know if you have any questions.